Okay, so this video is about the derivation for and using the surfaced area formula. Okay, using it is relatively straightforward. We're going to, kind of do the same thing that we did for the arc length formula. We're going to have the calculator do a lot of the heavy lifting for us. But I do want to talk about the derivation for this, because I talked about this a little bit when we were doing the arc length, is this idea that integration is not just area. Okay, it's a way of creating a calculation method really for anything that you want to find that you can set up into a limit of a sum involving delta x. So let's take a look at where this comes from. All right, so let's do a picture here of our f of x between a and b here. Okay, so there's our function. And let's see here. What we want to do is we want to rotate this around the x-axis. We create that mirror image there. And then look at a cross section here. Okay, and it's this area right along here that we're interested in. Now the issue, I tried to draw this so that you could see that this is not really a cylinder. Okay, the formulas that we're going to use to represent this surface area are going to come from the surface area of a cone. Okay, and we're missing the top of the cone, and so in fact this is going to be this surface area of what's called a truncated cone. Okay, so we'll come back to this in a few minutes. But I want to get started out. So the first thing really we have to do is talk about the whole cone. So if we have a whole cone that's set up like this, let's see here. This is R, the radius. This is called L, the slant height. And the idea here is that we can cut this cone and then open it up flat. And if we do that, we get something that is essentially a portion of a circle. Now this section right along here is the base of the cone. And so we know that the circumference down here is going to be 2 pi r. So that's this distance right here, 2 pi r. Now when we cut along this edge right here, we got those slant heights, L and L are right there, and then this central angle right here, we're going to call theta. Okay, so a couple things about finding the area of that sector, because what's inside here, this is a piece of a circle, but it's also, right, the surface area of that cone, excluding the bottom, and that's really what we're interested in. We're interested in the sides of a truncated cone, but to do that we need to get the surface area of that whole cone, but exclude the bottom of it. Okay? And so the area for the sector of a circle is going to be pi r squared times how much of the circle you have, right? If theta is 90 degrees, you've got a quarter of the circle. If theta is 180 degrees, you've got a half circle. So the question is, what portion of the circle are we working with? And so our area here is going to be pi. Our radius in this circle is L squared, and then times what proportion of the circle are we working with? Okay, I was talking in degrees a minute ago, but of course, since we're doing calculus, we need to do this in terms of radians. All right, let's see here. So these pi's cancel each other out, and this comes out as 1/2 L squared theta. All right, we're getting there. Let's see. I think I'm going to have to erase this diagram right here. But when it comes time to talk about it again, if I need to, I'll redraw it. So let's see. What else do we want to do? Let's see. Oh, we also want to relate theta and this 2 pi r over here. So just like we did with the area of this piece right here, we also want to think about this length, that length of that part of the circumference. So again, it's going to be proportional to the whole circumference. And so let's see here. So this is going to be equal to 2 pi times the radius of that circle, which is L, and then times the proportion pi over, theta over 2 pi. So these 2 pi's cancel each other out. This is L times theta, and we know that that's equal to 2 pi r. So that says that theta is then 2 pi r divided by L. So we're going to now come up here and replace that theta with 2 pi r divided by L. Let's see, the 2's cancel, one of the L's cancels out, and what do we come out of this with? Pi L r. Okay, so that's for the whole cone. That's for the whole cone. Right? So I mentioned a minute ago, what we're really interested in is what's called a truncated cone. So let's set this up. This is going to be a big R. This is going to be a little r. And let's see, how did I label the slant heights? Let's see here. This one I called H, and then this piece down here I called L. So that's a little bit different from this L right here, but that's just kind of the way things go when we're trying to assign parameters. So if we're interested in this surface area, we want the surface area for the whole cone, which, let's see here. Let's see. That's the big cone. That's going to be pi, and then that whole slant height is h plus L, and then the radius down on the bottom there is the big R. And then the area for that little cone is going to be pi, its slant height is h, and then its radius is little r. Okay, so let's see here. Now I'm going to have to erase a bunch of this over here. Okay, so the surface area of this truncated cone is going to be the whole cone minus the little one. So this is the area for that truncated cone piece. So that's going to be the big one, pi, h plus L times big R minus pi h little r. Okay. Now what? We're going to do some substituting here. Let's see here. Let's pull out the pi, factor out the pi, and then we'll have big R h plus big R L minus little r h. Okay. Now we need to talk about the similar triangles that live inside this cone, right? You've got a similar triangle here and here. Okay, these are actually right angles. It's poorly drawn, but they are. So because of that, that h over r, little r, is going to be equal to h plus L over big R, right? Because those are similar triangles. Now, let's see, what do we want to get out of that? We're going to cross multiply h times big R equals little r times h plus L. And then let's see here. So this is RH plus RL. And what we want is the big RH minus the little RH equals little RL. Okay? So we're going to come over here now and we're going to substitute in for that big RH minus little RH. We're just going to replace that with little r times L. So this is pi, big R times L plus little r times L. And having done that, we can now factor out the L and this is big R plus little r. Okay, let's see here. I need that diagram again. Well, let's draw another one. So, here's our function. And let's see, what are we doing? We're going to rotate this kind of like that. Okay, so this is really our little r right here. Okay, and then our big R is going to be down in here. And because this thickness is a delta x, all right, then the trick is that this is going to be skinnier and skinnier, and we can identify kind of this, the difference between big R and little r is going to become negligible, and we can create this average of those two called r star, which is the average of those two radii. And so now to introduce that into this formula, we're going to multiply by 2 here and divide by 2 here. And so now what we've got is this area, surface area for that truncated cone is going to be 2 pi L times r star. Okay, so now we want to start summing this, right? Because this is going to be each of these little sections surface area, okay? So that's the surface area for each of these little sections in here. So let's see, let's do some more erasing. I'm going to get rid of all this stuff here. Okay, so now we want to sum this up. So we want to sum, all right, as I runs from 1 to n, take the limit as n goes to infinity. We want to do 2 pi L r star. Okay, so the r star is essentially f of x, right? That's the function value right in the middle of this little interval, okay? So that's the r star. So we can replace that, let's see here, 2 pi instead of r star, we're going to have f of x sub I. And then the L, okay, is that slant height, okay? That's that distance right there, which is actually the arc length. That's why this piece comes in, is because the arc length there then is square root 1 plus f prime of x sub I, all squared delta x. All right, there's our sum. Take the limit as n goes to infinity, and now we get an integral, and this is 2 pi f of x, and then we get the arc length formula in there, 1 plus f prime of x all squared dx. And there's our formula. Okay? This is a little bit tricky, but again, mostly what I'm asking you to do is just to use the formula. I don't like to give out formulas without talking about where they come from, because that is an important aspect of math. Okay? If you struggle to understand this, don't feel bad about it. It is kind of challenging. Okay? But I just do want to put it out there. I think it's valuable to hear it, even if it is complex and difficult to understand. Okay, so let's take everything back down and just go to the formula, and we'll look at a couple example problems, and then we'll also look at that Torricelli's trumpet issue when we get done with the sample problems. Okay. So we're going to use the same problems that we did the arc length for. So for example, let's see here. Let's say we do problem 4. This is y equals x squared plus x minus 2, and we're looking at the region for x greater than -2, but less than 1. All right, let's see here. What is that? So that's going to have roots at, I believe, -2 and +1, so kind of something like this. Right, and there's the roots right there, that's why I chose those. And then we're going to rotate this around the x-axis, and it's going to make a little sort of Christmas ornament ball-shaped thing that looks like that, and we want to find its surface area. Okay. So in order to do that, we've got the function value, we need the derivative 2x plus 1, and then we want to set up the integral. We're going to integrate from -2 to +1, and then 2 pi x squared plus x minus 2 square root 1 plus 2x plus 1 all squared dx. All right, so now we're going to enter this as our function, 2 pi parentheses x squared plus x minus 2, and then square root 1 plus 2x plus 1 all squared. And that ought to do it. And I encourage you to double check what you've entered when you've got technology doing most of the work for you. Okay, so that looks good. And again, remember that this graph and what this graph looks like are going to be two different things. This graph is actually doing something very much like this. So let's see if we can go in and find our integral there. And the answer is going to come out negative because our original area was negative. It was under the x-axis, but really what we want is just an absolute value here. So this is going to be about 44.88. Okay, that's problem 4. Let's see here. Well, let's look at problem 10. Problem 10 is that 1/3 x cubed function. And we're interested in the region between -2 and +2. Okay, so 1/3 x cubed is going to be a little bit less than the x cubed function. Let's see. So where x is 2, this is going to be 8/3, and where x is -2, this is going to be -8/3. So if we take this around the x-axis, what we're going to get is a couple of these sort of Hershey's Kisses looking things, okay, with their tips connected. And so we're looking for the surface area of that figure, which is, you know, it's going to be kind of something like that, okay? All right, so we've got our y. Y prime then is going to be 1x squared, okay? And so our integral is just the integral from -2 to +2. Now, as I'm starting to write this down, let me just tell you it's something that I think is going to be happening when I do this, okay? Let me redraw this function here quickly. Notice how this area is below the x-axis, but this area is above the x-axis. It looks symmetrical. It looks to me like these are going to cancel each other out, okay? So I'll write this integral, 2 pi 1/3 x cubed, and then square root 1 plus x squared all squared, okay? I suspect that when I put this into the calculator, it's going to give me an answer of 0. Okay, I think we're going to get two symmetrical pieces of area with one positive and one negative that cancel each other out. So let me go ahead and calculate this and see what I get. And then if that's the case, what we can do is we can come back and integrate from 0 to 2 and then just double our answer. So let's see, 2 pi x cubed over 3, 1 plus x squared, all squared. And let's see, so this thing, what is this graph going to look like? Yeah, this graph is doing this. And so if I integrate from -2 to +2, those things are going to cancel each other out. So let's see what we get there. Yeah, so that's giving me 0. All right, so let's go back in and do it again. This time I'm going to integrate from 0 to 2, and I'm going to double that. So 2 pi, it's the same thing, x cubed over 3, 1 plus x squared all squared dx. So let's see what we get for that. 0 to 2, that comes out as 24.118. Okay. If we double that, we get approximately 48.236. Okay, so that's what we're working on for the surface area. Now let's step back and look at this Torricelli's trumpet, which is, or Torricelli's trumpet, or Gideon's horn, or whatever people call it. So what is this? This is what happens when you take the function y equals 1 over x, and we cut it off here because it's got that asymptote. We cut it off at x equals 1. This is the point 1, 1. And then we create the figure, what happens when we rotate this area that keeps going out, rotate it about the x-axis. That's why they call it a trumpet, is because it sort of looks like that. Okay. And this thing just keeps going and just keeps going. And you can see that it's approaching 0, right? That thickness right there is approaching 0, but never actually equal to 0. So if we set up, let's see here, the volume here, the volume is, we've just got a single radius here, right? Our area was under here, it was flush up against the axis of rotation. So this is just a disk. We're starting at 1, we're going out to infinity, and it's going to be pi. Our radius is 1 over x squared dx. Okay, so pi 1 to infinity, that's going to be x to the minus 2. So that'll be x to the minus 1 over minus 1. So let's see what we get here. Limit as a approaches infinity. We've got the pi there. This is minus 1 over x from 1 to a. Oh, yeah, let's see. Okay, good. So limit as a approaches infinity, pi minus 1 over a minus 1 over 1. So this is going to be a plus 1 right here. And as a goes to infinity, that thing's going to go to 0. And so this thing comes out as pi. Our volume is finite. It has a volume equivalent to pi. Okay, well that's kind of interesting. Now, let's look at the surface area. Our surface area is the integral from 1 to infinity. 2 pi, our f of x is 1 over x, and let's see, square root 1 plus, the derivative here is, let's see, if y is x to the minus 1, y prime is going to be negative x to the minus 2. So, let's see here. So this is going to be minus 1 over x squared, all squared, dx. Let's see here. So this is 2 pi, 1 over x, square root of Let's see here. 1 plus, and we can leave it like that, but it's going to come out as 1 over x to the 4th power. Now, let's see here. How do we integrate this? Because this is tricky. That last one I could do myself, whereas this, let's see. What if we take the calculator here and we go in here 1 over x and then 1 plus 1 over x to the 4th. Okay. All right, well, let's see what this graph looks like. It actually looks very much like the original graph there. It's kind of doing this. So what if we go in and try to find our integral from 1, let's say 1 to 100. Okay, so if we do this integral from 1 to 100, it did not give me a good value there. Let's try this again. Take the integral from 1, let's try 1 to 10. Oh, I think that 100 was off the screen. Okay, so that's going to be 15.2. That's going to be 1 to 10 is going to be 15.2. Now, to do the integral out to 100, I think I have to make my x maximum 100 on here. So now we get a new graph, and this time the graph goes out to 100. So let's see if we can calculate what that is. From 1 to 100. Okay, 29.645. Okay, let's do this one more time. One to 1,000. This might take a little while to calculate. What do we get there? 44. Okay, so it's growing pretty slowly. If I had the other, I think I've done this in the past with that graph software. Graph software also calculates area under a curve for you, and it's a lot easier to go in and change the values, and it will quickly adjust these values. But you can see that these things are growing, and I think as far as I go out, it seems to be picking up an area of 15 for every power of 10, right? So from 1 to 10 is 15, from 1 to 100 is almost 30, from 1 to 1,000 is about 45. Maybe I'll do one more. Let's go out to 10,000 and let's see if we get something close to 60. So let's change this to 10,000. Give it a minute to graph that. And then we'll go in and calculate the area from 1 to 10,000. Put that down for a sec because it's going to take a minute to calculate that. $58.58, yeah. So this seems to be a pretty clear pattern that it's picking up a surface area of 15 units for every power of 10 that we increase, and it doesn't seem to be stopping. Okay, so this improper integral diverges. Okay, it does go to infinity, and so that's kind of a sort of a paradox about this figure, is that it has that finite volume, but it's got this infinite surface area. And that kind of gets into some aspects of fractals. Fractals sometimes have that capacity There are these things that they call piano curves after this Italian mathematician Piano. And these things they're infinite lines, right, that go like this, but they're within a finite area. Okay, so when you step up a dimension, you go from having an infinite line in the interior to having a finite area in the exterior. And so this is the same thing. We've got an infinite surface area, but it encloses a finite volume. One thing I saw about the Torricelli's trumpet, people like to say that you could fill this with paint, but you would never have enough paint to paint the outside of it. So I thought that was kind of funny. Okay, so like I said, in doing the problems, we're really just mainly using this formula, and then we're going to the calculator to having that calculator find the integral for us. We'll get back into doing most of the work ourselves in the next topic, which is going to be center of mass. And so we'll see you then.